Today I will be doing two problems on Francis turbine. The first will be a basic problem on the concept of Francis turbine, and the second will be based on the draft tube. So let's start with the first problem. Let me read out the problem. A Francis turbine has a diameter or the runner diameter of the Francis turbine is given as 1.4 meter and it rotates at 430 rpm. Water enters the runner. So, the rotational speed of the runner is 430 rpm and the diameter of the runner is 1.4 meter. Water enters the runner without shock with a flow velocity of 9.5 meter per second and leaves the runner without whirl with an absolute velocity of 7 meter per second. The difference between the sum of the static and the potential heads at the entrance to the runner and at the exit from the runner is 62 meters. The turbine develops a power of 12.225 megawatt. The flow rate through the turbine is 12 meter cube per second with a net head of 115 meters. So, we have to find out the absolute velocity of water at the entry to the runner, the angle and the angle of the inlet guide vanes. Also, we have to find out the entry angle of the runner blades and the loss of head in the runner. So, first let us see the velocity diagram for the Francis turbine at the outlet and at the inlet. So, this is the velocity diagram at the inlet. This is the tangential velocity at the inlet or the whirl velocity at the inlet. This region represents the peripheral velocity of the runner blade at the inlet. This angle represents the inlet guide vane angle and this angle represents the runner blade angle at the entry or the inlet. This is the relative velocity or VR1 at the inlet. This is the flow velocity at the inlet or VF1 and this is the absolute velocity at the inlet of the runner, that is V1. So, this is the inlet velocity diagram. So, basically in the first part we are required to find out the absolute velocity at the inlet, the absolute velocity of water at entry to the runner, that is V1. So, first let us see what are the parameters that are given. So, first the diameter of the runner is given as 1.4 meters. Second, the rotational speed of the runner is given as 430 rpm. Next, it is given that water enters the runner without shock with a flow velocity, that is Vf1. The flow velocity at the inlet is given as 9.5 meters per second. The absolute velocity is given at the outlet as 7 meter per second. Next, it is said that the difference between the static and the potential heads at the entrance to the runner and at the exit is 62 meters. That is the sum of the static and the potential head, that is the potential head or the static head at the inlet to the runner is given by P1 by rho g and the static head the potential head at the entry is given as Z1, that is the elevation at the inlet to the runner, minus the static head at the outlet to the runner is P2 by rho g plus the potential head at the exit of the runner is given by Z2. So, this whole difference is given as 62 meters. Next, the power developed from the turbine is given as 12.25 megawatt. The flow rate is given as 12 meter cube per second and the net head available is given as 115 meters.
So, from this velocity diagram, we see that the absolute velocity at the inlet is the square root over the tangential velocity at the inlet whole square plus the square of the flow velocity at the inlet. That is, we are applying Pythagoras theorem to this triangle. So, the flow velocity at the inlet is given as 9.5 meter per second. So, we are required to find out the tangential velocity at the inlet. In order to find out, we use the basic relationship, that is the power developed by turbine is equal to the power supplied to the runner by water. So, the power is equal to P is equal to rho Q into V W1 into U1. U1 is the peripheral velocity of the runner blade at the inlet minus V W2 into U2. Now, in the problem, it was said that the flow at the outlet of the runner blade exists radially, that is, the tangential component is 0. So, we are left with now in this relationship, the only unknown right now is the peripheral velocity of the runner blade at inlet, that is U1. The other quantities, that is Q, is given in the problem. We know the density of water as 1000 kg per meter cube, and we are also required to find out the tangential velocity of at the inlet. The power P developed is given. So, U1 is given as pi dn by 60. That is, U1 is equal to pi dn by 60, where d is the diameter of the runner blade, which is given, n is the rotational speed of the runner, which is also given. The diameter of the runner is given as 1.4 meters, and the rotational speed of the runner is given as 430 rpm. Substituting these values, we get the value of the peripheral velocity of the runner blade as 31.5 meter per second. So, from this relationship, right now we know the value of U1. So, we find out the value of the tangential velocity at inlet as P by rho Q into U1. So, substituting the values, we ultimately find the tangential velocity at inlet as 32.4 meter per second. So, finally, returning to the basic formula for the absolute velocity at the inlet, VW1 square plus VF1 square. So, substituting the values here, we ultimately get the absolute velocity at inlet as 33.76. Also, we are required to find out the value of alpha 1, which is the inlet guide vane angle, and clearly from this velocity diagram we see that alpha 1 is equal to the tan inverse of VF1 by VW1. that is alpha 1 is equal to tan inverse of V f 1 by V w 1. Substituting the values, we ultimately get the value of the inlet guide vane angle as 16.34 degrees. Next, we are required to find out the runner blade angle at the inlet to the entry, that is beta 1. So, beta 1 is given as the tan inverse of V f 1 divided by this part, this length, which is actually V w 1 minus u 1. So, beta 1 is given as tan inverse of V f 1 by V w 1 minus u 1. We know the flow velocity at the inlet, we know also know the tangential velocity as well as the peripheral velocity of the runner at the inlet. So, substituting the values, we ultimately get the value of beta 1 as 84.6 degree. So, right now, let me return to the outlet velocity diagram. Since we are told that the velocity at the outlet or the water exits the runner radially. So, guide vane angle at the outlet is 90 degree and V w 2 is equal to 0. This is the runner blade angle at the exit. This is the peripheral velocity of the runner at the exit. This is the relative velocity at the exit and this is the absolute velocity of water at the exit. So, finally, what we are required to find out is the loss of head in the runner. For that, we write the basic relationship of the head available, that is head available at the inlet of the runner is equal to head available at exit of the runner plus the head lost in the runner plus the head that is used up for the work done by the turbine. So, if we represent the inlet to the runner by suffix 1 or subscript 1, that is subscript 1 represents the inlet to the runner and subscript 2 represents the outlet to the runner. So, the head available at the inlet we can represent it by H 1, the head level available at the exit of the runner we are representing by H 2, the head lost in the runner that we are required to find out is H f, and let this be represented by H w. So, the head that is used up for the work done by the runner is actually the work done per unit weight of the fluid, which is actually given by V w 1 into u 1 minus V w 2 u 2 by g. Again this is 0 as V w 2 is 0. So, we are left with we know the values of V w 1, u 1 and g. So, we can find out the value of H w. So, we can write H f as H 1 minus H 2 minus H w. So, H 1 now can be written as P 1 by rho g plus V 1 square by 2 g plus Z 1. H 2 is P 2 by rho g plus, that is the pressure head, plus the velocity head at the exit plus the potential head. So, H 1 minus H 2 is, we can write it as P 1 by rho g plus Z 1 minus P 2 by rho g plus Z 2 plus V 1, that is the difference in the velocity head. Now, this part it is given as 62 meters in the problem. So, and we are, and the velocity, absolute velocity at the outlet is also given in the problem. It is given as 7 meters, and V 1 I think we have found out, yes, V 1 was found out as 33.76. So, 33.76 square minus V 2 value is 7. So, 7 square. So, we get the value of H 1 minus H 2. So, ultimately we get the value of H f as H 1 minus H 2 minus of H w. We know all the values we have already found out. So, substituting all the values, we ultimately get this loss in head as 13.45 of 13.45 meters. So, we have found out all the quantities in problem 1. Now, let us move on to the next problem, which is based on the draft tube. So, let me read out the problem. The following data refer to an elbow type draft tube. The area of the circular inlet is 25 meters square. The area of the rectangular outlet is 116 meters square, and the velocity of water at inlet to the draft tube is 10 meter per second. The frictional head loss in the draft tube equals 10% of the inlet velocity head. Elevation of the inlet plane above the tail race level is 0.6 meters. So, we have to determine the vacuum or the negative head at the inlet and the power thrown away in the tail race. So, let us write down the quantities that are given. Before that, let me show you a schematic of the draft tube. So, this is the draft tube, this is the tail race, and we will be considering this as the datum. This is section 1 or the inlet to the draft tube, and we are considering the tail race as the section 2. This is the elevation of the inlet of the draft tube above the tail race level, which is Z. So, since we are denoting the inlet section of the draft tube by subscript 1, we write the area at the inlet A 1 as 25 meter square, and the area at the outlet is given as 116 meter square. The velocity of water at the inlet to the draft tube is given as V 1 is equal to 10 meter per second, and the frictional head loss in the draft tube equals to 10% of the inlet velocity head. That is, we know the inlet velocity head, that is Hf, we know the inlet velocity head is V1 square by 2g, and 10% of this, that is 0.1 into V1 square by 2g. So, this is the head lost in the draft tube, frictional head lost, and if we find out the value, it comes out as 0.51. We know the value of V1, 0.51 meters. Next, we are given that the elevation or Z of the inlet of the draft tube above the tail race is 0.6 meters. So, first we have to find out the negative head or at the inlet. So, let us apply Bernoulli's equation between these 2 points. Before that, let us apply the law of continuity or the conservation of mass between these 2 points. So, we can write at the inlet, we can equate the mass flow rate at the inlet and the outlet, and we can write rho 1 A 1 into V 1 is equal to rho 2 A 2 into V 2. Since rho 1, since the density is constant, we are considering constant. So, we can finally write A 1 V 1 is equal to A 2 V 2. We know the inlet area and the outlet area, we know the velocity at the outlet, sorry, we know the velocity at the inlet. So, we can find out V 2 as A 1 V 1 by A 2, which comes out to be 2.155 meter per second. So, now let us apply the Bernoulli's equation between section 1 and section 2. So, we can write P 1 by rho g or the pressure head plus the velocity head at the inlet plus the potential head is equal to P 2 by rho g plus V 2 square 2 g plus, since we are considering the datum at the section 2 itself. So, the elevation is 0 plus the head lost, which is H f. Now, since all the pressure, we are considering all the pressure in this pressure head in this, as the all the pressure that we are considering in this equation are the gauge pressures, that is the pressure above the atmospheric level. So, since the at the section 2, this section is exposed to the atmosphere. So, this is nothing but the atmospheric pressure. So, we can take this as 0. So, ultimately the pressure head at the inlet can be written as minus of Z minus of 1 by 2 g V 1 square minus V 2 square plus H f. So, we know the value of Z, it is given as 0.6 meters. We know the value of both V 1 and V 2, and we have find out the value of H f as 0.51 meters. So, substituting all the values, we ultimately get the value of the negative pressure head as minus 4.95 meters. So, there is a suction pressure at the inlet, and so suction pressure head at the inlet of the draft tube is 4.95 meters. Next, we are required to find out the power that is thrown away in the tail race. So, as you can see that at the exit of the draft tube, the velocity is not 0. So, whatever energy at the exit is lost due to the kinetic energy at the outlet. So, the power that is lost, or the power lost due to the kinetic energy, can be written as, that is the second part, rho q into g into V 2 square by 2 into g. So, substituting all the values here, we know the value of q, that is 1000 into q, that is what is the value of q? The value of the value of q is nothing but the product of A 1 into V 1 into 9.81 V 2 we have found as 2.155 square by 2 into 9.81. So, this comes out as 580.5 kilowatt. So, this power is lost due to the velocity head present in at the exit of the draft tube. So, with this ends the second problem.